Welcome back, chemistry fans. Today, what we're going to do is Unit 2, Topic 3. But the problem is we're actually calling this Topic 5 now because I've laid out this is the 5th day of a new and different topic. What we're going to talk about is something called Lewis structure. It's very similar to what we did last time with the electron dots, whereby this time we're going to try and show the molecular shapes, the molecular structure in 3 dimensions. So we're going to try and get the bonding to be more representative of what it looks like in real life. So let's share our screen and get started on this process. Okie dokie. So in this bonding, we need to remind ourselves that the electrons are being shared, that there are 2 electrons for every bonding pair. For every bond that occurs between 2 atoms, there would be 2 atoms now, or 2 electrons. It can be that there would be also 4 electrons or even 6 electrons. We cannot have 8. That just doesn't exist. There's not enough room for that. But there is enough room in between the atoms for 2, 4, or 6 of the electrons to fit in there. So we would call that single bond, double bond, or triple bond. But the goal of all bonding is to achieve a stable octet, unless you're hydrogen, which only wants 2. So let's jump into this right now. So how we have done this before is we have placed valence electrons around the elements where they have 1, 2, 3, 4, 5, 6, 1, and 1. But what we got to change now is the idea that these electron dot structures are where the electrons belong. That was just a representation. It's not accurate. Whenever they then start to become molecules, we lose their positioning according to those rules that we established for individual elements. So now what we're trying to do is show how they bond. So what I'm going to do is I'm going to move this electron. I'm going to move that electron over here to show that it is bonded with this electron. They are sharing. And I'm going to move this electron over here. Now what I have got is a more accurate representation of the molecule for water. What we can do, though, is instead of drawing those dots, we're going to now draw them as dashes. Anytime there is a bond between 2 atoms, we will just simply draw that as a dash. This is a complete Lewis structure. It would be nice if you would include the extra electrons, which are not bonding, as they will play an important role whenever we start talking about their geometric shape. Let's do another one. It's the exact same end game here. So I'm going to first draw out my electrons for valence purposes. 1, 2, 3, 4. Now, why did I not do it in order? Because I know that these are going to bond together. So I'm saving myself a step. And what I have here now is hydrogen has 1 valence electrons. The sulfur has 6. So I can redraw this now as single bonds between these atoms, replacing my extra electrons where they belong, top and bottom, so that it represents more accurately what this molecule should look like. All right, let's do the same thing down here. Now, one of the neat things that you can start to learn is anytime you have a halogen, halogens are in the 17th column of the periodic table. So if we were to take a quick glance over at the 17th column of the periodic table, we would notice over here on the far right side, all of those elements called halogens, they have 7 valence electrons. They are only interested in gaining 1 more valence electron, meaning that they will always have single bonds. The same is true for hydrogen. Hydrogen has 1 electron. It's only interested in gaining 1 more electron to give it 2. It will only have single bonds. So that's going to actually help us as we are trying to draw out these Lewis structures for these molecules, because what we now can say is, oh, I don't need to do the valence electron counting. I can just simply draw my bonding lines. And I can then replace what is left over, because I know that all of these chlorines actually have to have 8 electrons around them. The carbon in the middle, it has 8 because of the bonds. 1, 2, 3, 4, 5, 6, 7, and 8. All right, now, what if things don't work out nicely? Oh, well, here we got one more, and then we'll get into the main ones. So this one, same thing. The hydrogens I know have single bonds. I know that those hydrogens all have stable duets, so they're okay, but it's the nitrogen that does not have a stable octet. So I need to incorporate two more into its structure to give it the stable octet that it's looking for. So if I look around it here, there is a stable octet. The hydrogens each have stable duets. Everyone is satisfied according to their octet or duet rules. Now, how we can represent double bonds, you will notice over on the right, you'll see two lines. If there happens to be four, and you're saying, well, when would there be four? Well, let's jump into that. Notice this molecule. How would I know that there is a double bond instead of a single bond? Well, we're going to have to rely on some math formula. So at some point, you have to start trusting this formula. 1 minus half equals the bonding electrons. Want means the valence electron. I'm sorry, want means that it wants 8 valence electrons. Hydrogens only want 2. So for this example here, if I'm going to do want, the want is 8 for the carbon, 8 for the oxygen, 2 for the hydrogen, and 2 for the other hydrogen. That's a total of 20. Now the have in the formula is the valence electrons. Carbon has 4 valence electrons, oxygen has 6 valence electrons, and the hydrogens each have 1. If I subtract those two values, it gives me 8. That's the number of electrons that are in the bonds, but that doesn't tell me how many bonds. So I divide by 2 because each bond has 2 electrons. And that tells me that there are 4 bonds. Now, I just told you the rule that hydrogens always have single bonds. So that means that the third and the fourth had to come in between the carbon and the oxygen to give it a double bond. So trust the want minus have formula, otherwise you will be guessing incorrectly. Let's do a couple of examples down here. Now, let me do those first ones here. Let me do one on each page. The first one, what we notice about these molecules, the way they are written, they are trying to tell you that the first element is always going to go in the middle. Now, as far as where you place the other hydrogens, it does not matter, but the hydrogens cannot bond to other hydrogens because they only want single bonds. Now, going back to that idea, I know that all of the hydrogens want single bonds, but I don't know what's going on in between the two carbons, so I must do want minus have. So want, each of the carbons wants 8. Each of the hydrogens, they want 2. So that is a total of 24. The have, the hydrogens each have 1. The carbons each have 4. If I subtract, I get 12, divide by 2, and that tells me the number of bonds. So I have 1, 2, 3, 4, 5, 6, 7, 8, or I have 4 bonds. So that means I need to have a double bond in between here. 1, 2, 3, 4, 5, 6. I had to have 6 bonds. I needed those 2 in between there, and you would not have known that unless you did the math to show me that. One more example. HCN. Now, in this case, please do not put the H in the middle because hydrogens can only bond once. So it's an acid, and that's why the H is first. So they're not trying to confuse you. They're trying to tell you it's an acid first. So we'll just go with the second element goes in the middle. Now, want minus have. Want, the hydrogen wants 2, the carbon wants 8, the hydrogen wants 8. That's a total of 18. For the have, I've got 1 for the hydrogen, I've got 4 for the carbon, I have 5 for the nitrogen. That's a total of 10. The difference between that is 8. That means I know the hydrogen can only have a single bond. But I'm looking for 4 bonds. So that means there had to have been a triple bond in between the carbons and nitrogens. This is everything that I wish to share with you about how to draw Lewis structures. You must trust this formula, want minus have, and then divide it by 2 to find out the number of bonds. Thank you so much for your time today. We will talk again soon. Bye-bye.